Right, so we have to discuss 2018 essay part. So we will start without consuming much time. So I will share the screen for you guys. I hope you can see the screen sharing. So first part, again, as usual, so there will be some statement to choose correct or wrong. Then there will be some questions related to the hybridization, Lewis structure, and all those things. Then they will ask some question related to periodic properties, and yeah, so it's the normal way that every time it goes. So without much time, we will start the lesson, the discussion for today. So we have to choose which one is correct and which one is wrong. The first one, the polarizability of the halide ion increases with increasing size. So we have discussed this many times. So polarizability, you know, for a cation, we expect a cation to be higher charge, high in charge, and low in size, so that its polarizability is very good. But for the anions, we expect, again, with higher charge, but the size is reverse. Okay, so anion we expect large size, cation we expect a smaller size, but higher charge. For an example, like 3+ is really good. And even for anion, so we expect higher charge, like 3- for an example, it's really good. So always remember polarizability, smaller cationic radius and larger anion radius, and both of them will have higher charge. So that means polarizability is very good. And when it forms some compounds, like forming bonds with other elements like cation or anion, always remember they are more or like covalent in nature when the polarizability is very high. So what happens to the halide ion increases, even increasing the size. So it's true, because when you go down a group, so basically you think about that. So the size of the halide ion increases without changing the charge. But for an example, group 7, but you see every time when the size increases, the polarizability is increasing more and more. So this statement is okay, right? Don't put tick, you need to write true. Okay, then the second one is ONO bond angle of NO2 is greater than that of NO2 minus. So it is conceptual. Think about this. Now, NO2 minus, what do you think about NO2 minus? So you see there is an additional electron than here, right? So for an example, when you think about the Lewis structure of NO2, so there will be one lone electron that is occupying the nitrogen. So the additional electron might be given to the nitrogen. So it can maybe in the nitrogen or maybe in oxygen. So you have to draw and see how the Lewis structure varies when you go from like NO2 plus, NO2, and NO2 minus. Okay, so do that, NO2 plus, NO2, and NO2 minus, right? Then think about the bond angle. For an example, NO2 plus, so it's like a linear structure, 180 degrees. And then you go to NO2, so there will be one lone electron. So when you go from NO2 minus, there will be more electron repulsion. So yes, so obviously this statement is correct. Okay, so you have to write it is true. Right, so the third one, London dispersion forces among CCl4 molecules are smaller than London dispersion forces among SO3 molecules. So they are talking about the dispersion forces. First, think about the difference in the molecular weight. So there's a big difference between the sulfur SO3 and CCl4. CCl4 is very high. But moreover, think about the London dispersion force. So London dispersion force is like a dipole, induced dipole. So it is an induced dipole interaction. So think about the arrangement of SO3. Right, so SO3 molecule is like a trigonal planar, and it's a planar structure. So there are not much of a degree that this electron crowd can be like depolarized to a certain direction, like inducing the polarizability. So, But for CCl4, like a tetrahedral structure, there are many degrees of freedom that you in different directions. So since it is tetrahedral, you can change its electron clouding within the bond by using the one of the other molecules because of its higher bonds. One, because here there is 3, there is 4, and the spatial arrangement is very efficient to give a nice London dispersion force, right? So the CCl4 will have a higher London dispersion force than SO3. So this is false. And fourth one, the shape of HSO4 minus ion is trigonal bipyramidal. So this is directly from H2SO4. So basically there should be like a OH group here and the rest of the oxygen. So there will be double bonded one, another one here, and another one here. The valency of sulfur, 1, 2, 3, 4, 5, 6 electrons covered here. And this is the negative charge. So you see here, when you check the shape around sulfur, so it will be 1, 2, 3, 4. So it's basically tetrahedral. But when you go here with respect to this oxygen, so you see it's a band. So to which atom that you think they are asking, the shape of the HSO4 minus ion is trigonal bipyramidal. We still don't see trigonal bipyramidal, so this statement is wrong basically. But it's sulfur, it is tetrahedral. With respect to oxygen, it is bent. So they have to specify that. You cannot just tell this is some shape. Okay. They have to specify, like for an example, in these three structures, you see shape around carbon 1, nitrogen 2, carbon 3, P4. So you have to specify like that. Right. So question number 5. All 3D atomic orbitals of an atom are represented by the quantum numbers. So 3 means N should be 3. D means L can be 2, yes. So, and ML, which is from minus L to plus L, including 0. So they have only mentioned only 1. So it is not good, right? Because ML generally goes from minus L to plus L, including 0. So we typically call them as 2L plus 1. Okay, the values. So you cannot just give this 1. 1 is there, but you cannot just give 1 value for this 3D atomic orbital. You have to specify all for an example, right? So this is not true. And the last one, the addition of an electron to a gaseous phosphorus atom is an exothermic process. Yes, so check about the electronic configuration of phosphorus, whereas for a gaseous nitrogen atom, it is an endothermic process. So think about the difference between nitrogen and phosphorus, right? Phosphorus, you see the gaseous phosphorus, normally when you check about this addition of the electron. So normally when you check about nitrogen and phosphorus, so you have nitrogen here and phosphorus, then arsenic, bismuth, and then bismuth will be there, then antimony and bismuth. So nitrogen, phosphorus, arsenic, antimony, and bismuth. So they are in the same group. So more or less, they will have the same tendency for the reactivity. But you see here gaseous nature. So nitrogen in gaseous nature, it will be like N2 with a great triple bond in it, right? So do you think that is the way that you are going to do it, or think about the way that phosphorus is generally represented as P4 molecule with single bond? So it's not that easy. Okay, so try to think about this more. How do you approach this one? Because nitrogen and phosphorus, when you think that, so nitrogen is 7, so basically it is 1s2, 2s2, and 2p, it is 2p3. So it's like a partially stable state, right? Phosphorus also. So you think that this could be like it's not easy to add an electron. Yeah, it is difficult to add for nitrogen, but not for phosphorus, because it's a little bit far away from the nucleus. Okay, so think about it. Right, so this summarizes the discussions. This is true, this is correct. In fact, these three statements, 3, 4, 5 are wrong, 1, 2 is correct, the last one is correct. So these are very basic things when you know your concepts really well. And part B, draw the most acceptable Lewis structure for the molecule SF3N. So we already saw the different structure of SEN minus, and in the MCQs they are asked for the most stable structure for SEN minus. So we drew 3 structures and 2 were possible, and then we went for the most electropositive atom, which can be present in the middle. So basically there should be fluorines, and sulfur is more electropositive than nitrogen, so sulfur will be in the middle like this, and you have to show all these fluorines as terminal atoms. That's it. And there will be this sulfur nitrogen bond, so nitrogen, it has to complete its octet, so there will be a triple bond, so that nitrogen completes its octet. Fluorine has to complete, so there is 7 electrons around fluorine, so 1 is added here, so no problem. And even sulfur is completed. So this is the structure. So show all the lone pairs of electrons for fluorine also. It is very essential when you draw Lewis structures. Otherwise, you will lose marks. Even sometimes they will not give marks. Okay, so be aware of that. That is very important. Right, so this becomes very straightforward then. And then the second one is based on this normal procedure. So here they have given a structure. What you have to do is draw 2 other resonance structures, just 2. So think about this structure and try to get an idea how can I draw the structure of this one. First thing that you can check here is, okay, so carbon, everything bond is okay, no charge, no problem. But what if you can give this electron to this carbon? Then if you give this 2 electron to this carbon, there will be a triple bond here. So around carbon, there are 5 bonds, so which is not acceptable. So this bond has to be to this side. So the first restructure that I can come across is this carbon will be triple bonded to this oxygen, and there will be a single bond here. But don't forget, here there will be a positive charge on oxygen. And then due to these 2 electrons given to this carbon, so there will be a negative charge here on this carbon. Okay. And this is then negative charge, so there is the double bond here for this one, and the rest is very similar. Okay. So I always tell you, when you draw the resonance structures, try to draw the electron flow. Okay, but don't forget, when you are drawing the resonance structures, still you try to complete the octet, okay, by giving different charges. There is no problem in that, right? So this is one of the structures that you can expect, right? So what else you can draw? The second one that I can think of is like, okay, so you give this, gave a negative charge here to the middle carbon. What if this electron pair is again given to the adjacent, the other one? So here we can do another one like this. So what I can do here is, okay, I give this to this one and I break this one. So it is also possible, right? So the next structure that I can draw here, so this part would be similar, like carbon triple bond and 2 lone electrons. So there will be this one, and there will be a triple bond now here between these 2, and there will be a single bond here, which makes this oxygen now negatively charged, and there is still the positive charge on this oxygen. Okay, so there are many ways that you can try to draw resonance structures. Even you can make these 2 a double bond and this 1 positive and 1 negative. It's really interesting when you try to draw different resonance structures. Okay, so there are only 2, but when you try to draw at least 5, I would say. So from here 1, 2, 3, so there you can draw 2 more. Okay, so try to draw the other 2 as well, because you are in the learning curve, so it's no problem of trying to draw other structures as well. Right, so these are the primary 2 structures that you can draw here within this part of the question. So if you want, you can draw the other ones, like giving triple bond here, and a single bond between this and this 2 carbons, and giving a minus here and minus here. And there will be a positive in this oxygen and positive in this oxygen. So plus, plus, minus, minus, and your structure is again neutral, so no problem in that. Or otherwise, you can try to make 2 double bonds here. You can just keep this double bond here and change one of it, so no problem in that one as well. So you can manipulate as you want, so you can draw different resonance structures. Right, moving on. So this question is very straightforward. We can go through very quickly because we have already discussed what is actually happening, what is the hybridization, what is the shape, what is electron pair geometry. So VSEPR pairs, as I have mentioned many times, this is the number of repulsion units. So here they are asking about carbon 1, 2, 3, 4, carbon, nitrogen, carbon, phosphorus. So it is very easy because the Lewis structure is also given. So here the Lewis pairs, it becomes 3 here. And for nitrogen, it's again 3. For carbon, it is again 2. And for phosphorus, it is again 4. Then the electron pair geometry. So this is trigonal planar, and this is also trigonal planar, and this is linear, and this is tetrahedral. And then shape, so trigonal planar, bend or angular, and this is linear, and this is again tetrahedral. So these are very simple things, right? Then the hybridization, so sp2, sp2, sp, and sp3. So these are very, very simple things now. You should be able to complete within 5 seconds, I would say. Okay, but don't forget, be critical, also be more focused onto what you are doing. All right, okay, because sometimes people might lost at some point of going very fast through a question as well. And then it's very similar, because when you know the hybridizations here, you automatically can understand what are the overlapping orbitals. So it becomes very, very simple. Only thing that I have to mention additionally in this particular question is they are asking for the hybridization with P4 and Cl, because others are common, we have seen here. So P4 here, we discussed this about the hybridization here is sp3. So the bond between phosphorus and chlorine, since this phosphorus is sp3, so it can be between sp3 and sp3, or either you can take this as always sp3 because of the hybridization there. And for this chlorine, you can even give this as 3p. The unhybridized p orbital of chlorine can be also bonded here. So for this particular answer, there will be 2. Either you can write sp3 or 3p orbital. Okay. And again, it will be very easy to find out the pi bonds. So it's very similar, right? So nitrogen, carbon, carbon, all are in 2p. So the pi bonds are formed by the unhybridized p orbitals. So this will be always 2p and 2p and 2p. But what about this phosphorus pi bond between carbon and this phosphorus? So think about a bit. Now here sp3 is formed. So what is remaining? So since this is sp3 hybridized orbital, so the unhybridized could be a d orbital. So because all orbitals of sp3 is used, since p phosphorus in the third, so you can even think about a 3d. Okay. The crucial point here is in the marking scheme, since you are not familiar with this thing, they even gave marks for people who did not write anything. So no problem in that, but don't forget there is always empty 3D. Okay. I have discussed this before. If you remember about the chlorides of nitrogen and phosphorus, I told you nitrogen will form in Cl3 but not in Cl5, but phosphorus will form PCl3, PCl5. So why it form PCl5? Because they have additionally 3d empty orbitals which can form bonds. So that's it. Right, so the last part of question number 1. So arrange the following in increasing order of the property given. So reasons are not required, so no problem in that. First, ionization energy. So this is always very simple. So you come from lithium, boron, then carbon, nitrogen, oxygen, then go with fluorine, then again comes back. It goes like this. So you know this is a zigzag shape. So this could be lithium for an example, and this is beryllium. Then for boron you come down, so carbon, nitrogen, and yeah, oxygen. So I missed something here. I will erase this part completely, and I'll draw it again. So this, carbon, nitrogen, then oxygen again. Then fluorine and neon. Then for the sodium, you come back right down, even below lithium. So that is how it goes, right? Then phosphorus again, a little bit higher, but not higher than here. What do you think? Is higher than here or less than here? Because here we have phosphorus and beryllium. So what do you think? Phosphorus is higher than beryllium or beryllium is higher than phosphorus? So don't forget here, phosphorus will be higher. And then it goes again like this, and comes down. Here it will be potassium. So this is very common. You should know this one. And when you get the trend, so there will be a sodium for group 1, which we tell it will be the very, very smallest one. And then it will be boron here, which is here lowest. Then will be beryllium. And then rest we have nitrogen and phosphorus. Okay, so these are, sorry, phosphorus and nitrogen. Phosphorus and nitrogen, so don't forget that. Right, so this is a little bit of a trend that you should know. So the second one is we have already seen this based on the electronegativity of the nitrogen atom. So you can go with the charge or either hybridization. So we often go with the hybridization. So when you think about the hybridization and charge, so these two, you see something very close similarity, and then these two, and this separately, this one, right? So this is, you know, it is like an sp2, but when you think about the lone pair, so it can be like sp3 with a charge positive. So obviously, when you think about the charge, so when you have a positive charge, which means you still like to get some electrons. So basically ammonia will be lowest here. Then there will be NH4 plus, which has a little bit higher tendency than ammonia. Then here you think about the fluorine, which should be most electronegative, and carbon will have a more positive charge. So you can think this compound should have the highest electronegativity basically. So this could be this one. And in between you have two, NOCl and NO2Cl. So think about the charge here, or even the hybridization after drawing the structure. So NOCl, how can you draw that structure? So then NO2Cl, try to draw the structure and try to analyze how this comes. And even you can see here there are two oxygens, so there will be higher charge here based on the number of atoms. So it is always like NOCl and then NO2Cl. Okay, so this is the correct option. Don't forget about that. And the last one, it is about quantum numbers of electrons in an atom. So we have to arrange based on the energy. So if you are given, try to like, if you are given to arrange them based on the energy, so energy, principal energy levels is going to be from the n, right? So when you have a higher n, it is always going to be higher. So if you check the energy values, you see here 3, 3, 3. Okay, then these two should come before that. The first two should be these two, because n is equal to 2. Then you go for L. So here you see L is equal to 0, L is equal to 1. So this should come first and this should come second, because this is like the P. And in the N again, it's same. So this should come third, this should come fourth, in fact, and this should come fifth. Right? So it should be the normal trend that you can arrange these things. Okay, so don't forget. So these are very, very simple things. So when you analyze question number 1, the first part is really straightforward with the theoretical stuff, and a little bit of, again, testing with your Lewis structure knowledge, and finally a little bit of periodicity. So these are very, very common things at this point of time, because you should have already mastered these things up to this point. Okay.